Section 1.5 is titled Variables and Expressions. So we're first going to define what we mean by the word variable. A variable is a symbol, usually a letter, used to represent a value that is variable, i.e. it changes, it's not constant, it's not always the same. Sometimes it's 2, sometimes it's 5, or whatever. Okay? So some variables that you use a lot are x and y, right, with equations. They're not the only variables. When you take like a pre-calc or a trig course, they like to use Greek letters as variables there. So you get theta and gamma and stuff like that. So it's not always even like English letters that are used. It can vary. But typically we do see letters used. When we talk about evaluating, the word evaluating means letting a variable equal a specific value. So sometimes I will hear people describe this as solving. It's not solving. Solving means you have something that's got an equation. This equals this, and you figure out what is x. That's solving. Evaluating means plugging in a variable as a specific number and simplifying. So we have an example here where we have 4t minus k. So t and k would be variables. And this specific one, they're giving us values to evaluate this expression with. So our t equals to 2. We'll replace the t in the equation. So we have 4 times 2. And then the k equals -3. We'll replace the k in the equation. So,
plus 3 since it's a negative. Okay.
yeah, it will be. I'm going to write it out longhand, but you're right. It's going to simplify just like you said. So we have, let me multiply it out so that everybody can make sure and see. So I have 4 times 2 plus 3, like Maxwell said. 4 times 2 is, plus 3 is 11. So the evaluated value, right? We evaluated it, and we got the number 11. We can do the same thing on the next one. It actually only has one variable. Its variable is just the a, but the a occurs more than once in the expression that we're given. So we have to evaluate in every location where the a currently resides. So I have 3, and then I have, a is -4. Please make sure you put the -4 in parentheses and square it, because I want you to remember that you're going to multiply -4 times -4 and not lose the negative somewhere along the way there and forget where it's supposed to be. Okay? And then I have -2 times, or -2 times, again, -4. And then plus my 4. Okay, we're going to talk more about orders of operations and things next, but we encounter this before it. So let me just remind you really quickly that we always follow one acronym anyways, PEMDAS. So parentheses actually means simplifying inside of parentheses first. There's nothing inside of our parentheses to simplify here, right? E means exponents. We do have exponents here. So the exponent that we have on this one is right here. I have my -4 squared. So what happens when I take -4 times -4? Yeah, it becomes positive, and it's a 16. So that's the simplification of my exponents on that step. So I've sort of checked off the P and the E. M and D, I've listed them beside each other because the multiplication and division don't have an ordering between them. It just means you move from left to right. So sometimes you might actually divide before you multiply, and that's okay. The M and the D together. Do you have a question, Jasmine? Yep. That's why it really matters that you've got the exponent on the outside of the parentheses. So I don't know if everybody could hear what Jasmine was saying, but if you aren't careful where your parentheses are around the -4, and you put the square inside of the parentheses or something like that, or you leave the parentheses off, it will spit out at you that you've got a negative answer instead of a positive answer. So be just aware of that. So at this point, we're ready to do our multiplication and division. So what is 3 times 16? 48. And then I've got negative 2 times negative 4. That's 8. And then I have my plus 4. And there was no division, so that step's done. And then we would do addition. And so what did you get? 60. That's probably right. That looks right. I don't have answers written down. Is that okay? Cool. All right. So you do need to be careful that you do things in the same order. There's nothing inherently right or wrong with whatever order it is. But in order for mathematics to make sense from when I do a problem and you do a problem and somebody over in Europe doing a problem or whatever, we have to have a convention that we're all using in the same way. So that's what order of operations is. It's the accepted order that has been decided beyond us so that when we work a problem that it makes the same, it gives us the same answer, I guess you could say, as anybody else. So this is the ordering that has been established. Now I've used this word already, both of these, all three of these actually. So let's actually fully define them. I used the word expressions just a moment ago. This is simply a mathematical statement using numbers, variables, and operations. So the previous two problems on 1 and 2, those are statements. 4t minus k is a statement. Is an expression because it's a statement. 3a squared minus 2a plus 4 is an expression because it's a statement. An equation and an expression are not the same thing. An equation has an equal sign. It's telling you that two expressions are equal to one another. So if there's no equal sign, you don't have an equation. And people say that wrong all the time. Occasionally I'll slip up and say it wrong too. We're just so used to seeing and saying equations that we kind of think that sort of is the word for everything, and it isn't. An equation has an equal sign. And solving, I mentioned this before too in comparison to evaluating. Solving means to algebraically manipulate an equation to isolate a single variable on one side. So it's working out an equation where at the very end we want it to say x equals a number, right? Or y equals a number. That's what solving is. So what we did before was evaluating. What we're going to do next on the next slide is solving. Are you guys ready to try one? Lovely. So I have a couple of examples here. We're not going to get x equals a number, y equals a number, but we're still doing what it says over here in this question, which is to isolate a variable on one side. So on the first one, you'll notice we have x, y, and z all together on the left. We've got the number 7 on the right. And it says we want to solve for z. We want to isolate z. So either we need to move the z or we need to move the x and the y so that we separate them. And there's sort of an inherent benefit to either direction. And so it doesn't matter to me which one you do. You'll get the same answer either way. So would you like to move the x and the y or would you like to move the z?
X and the Y.
Oh, we got both. So I think maybe naturally we would probably leave the z there and move the x and the y, but let me show you both options just so you can see how they work. So let's move the x and the y. So we're going to subtract the x and we're going to add the y because we're trying to undo where they are. In particular, what happens is that I now have x minus x, that's 0, and I have a y and a negative y, and that's 0. So that's how I'm moving them. And I'm left with a negative z on the left. And then on the right, I'm left with 7 minus x and plus y. I'm almost done. Why am I not done?
Because you have a negative, you have to multiply.
Yeah, there's a negative attached to the z, and so I've heard both of these statements said, you can either multiply or you can divide by -1. It doesn't matter which perspective you have. The idea is you're changing signs. Do you have a question, Jasmine? Okay. Every time you touch your glasses, I'm seeing your hand move, and so I want to make sure I'm paying attention. I'm so sorry. So I'll write it as division, but it doesn't matter which one you want to do. I get a z on the left, and all my signs change on the right. 7 divided by negative 1 is negative 7. Negative x divided by negative 1 is positive x. Positive y divided by negative 1 is negative y. So this is what I would get if I solved for z. Now let's say for a moment that you wanted to move it the other direction. So we would add a z if we wanted to move it to the other side. If I do that, I have now x minus y equals, because these add to 0, of course, equals 7 plus z. So z shifted away from the x and the y, but now it's associated with something else, so now I'd have to move my 7, right? So I would subtract the 7, and I'd have x minus y minus 7 equals z. I get the same answer. I still had a two-part problem. I either had that additional step at the end where I moved the 7, or had the additional step at the end where I divided or multiplied by negative 1. Okay? So whichever perspective you do it from, you're good to go. Any question on that? Okay. On number 4, we actually have an equation you might have seen at some point. I mean, I know you've seen it at some point. I just don't know how recent it was. Does anybody know what that's an equation for? It is the area of a triangle. Very good. You don't need to know that for the problem. I was just curious if anyone did. Yeah, so we're going to solve this for h. There's a couple of different things we can do. I'm not a super big fan of dividing by fractions. I think it makes things look really complicated and messy. So I tend not to divide by fractions. So clearly there's a 1/2 that needs to move, right? And it is totally acceptable to move it as division. You could divide by 1/2. But then you have a fraction inside of a fraction, and it's just, ugh. So instead of doing it that way, what I would be inclined to do is multiply by the reciprocal. And we talked about that last class period, right? The beautiful thing about multiplying by reciprocals is that that means that this goes away, and my fraction, actually on this one anyway, turned into a whole number. So right now I end up having 2a equals bh. You're right. And then we would divide by the b. So the b's here would cancel. And I would end up with, yes ma'am, 2a over b equals h. If it bothers you for me to leave the h on the left-hand side, you can move it to the right-hand side. It doesn't matter to me. So if you would rather shift this around and write it so that the isolated variable is always on the left, sometimes people like to see it that way, you know, more power to you. Go for it. But why do we need expressions/equations involving variables? Well, the reason we do, the answer to this question, is that equations and expressions allow us to take a complex real-world situation and give it order and clarity using the structure of mathematics. They allow us to find solutions in an orderly way. Are any of you taking like Success 101 this semester? There's a test that you'll take, a book that you'll read and a test you'll take, the Strength Finders test, correct? Did you guys buy a book called Knowing Your Strengths or something? I can't remember what the name of the book is. It's an absolutely fascinating book, by the way. You'll learn a lot about yourself. When I first started OBU, I had to take this too. And I can't remember exactly what it's called, but there's one in there that talks about this idea of structure and organizing. As you might imagine, that's myself. That's why you have a book of notes, right? It's why I have so much structure in place before you walked in the doors, which was not all related to our current, health crisis going on. That's just how I operate. And I think that is a natural implication of a lot of mathematicians, is that we think and operate in very orderly and structured ways. Please don't tell me you had a coach in high school who was not an organized math teacher. I'm sure you did. That's not what I'm talking about. But I think the more you see higher levels of mathematics with people, the more you see a lot of that organized and structure going on. And with lots of other people as well, too, by the way. It's not just mathematicians. But this sort of need for structure and organization is something that is inherent in mathematics. And it gives us the ability to take things that are really complicated and solve them in a way that has some natural processes involved in them already. So I'm going to give you some kind of ideas about that. I already typed that over there. Who knew? All right. So we're going to take a look at some examples of that structure that we can impose upon complicated situations. Our language, take our English language, and impose that structure upon it. So we have a couple of examples, and we're just working in this section, not necessarily because these are wonderful, great, real-world examples, but taking a look at the structure of language and how we convert. That's the idea. Junior has 6 brothers. Y of them, right, some number Y of those brothers, went to church. Write an expression for the number who skipped. So what would I do if I had 6 and Y in this situation, and I wanted to know how many didn't go to church? Yeah, you would subtract, right? This is just subtraction. Okay, so nothing in those words said you need to subtract. Nothing said find the difference between. Those are often words we see inside of context math, real math context problems. They're not real world problems, right? They're not. Now, if it hurts, or not hurts, but if it confuses you to see the Y in there, you could pretend it's a number and think what you would do too, right? Junior has 6 brothers, 2 of them went to church. How many of them skipped? Well, what would you do? You'd do 6 minus 2. So if you do 6 minus 2, then you do 6 minus Y. Does that make sense? Okay. A few others, just some real quick ones to translate the following into some algebraic expressions. 4 less than K. This is one that always confuses people because you have to switch the order. Yeah, so what did you have, Maxwell?
K minus 4.
Yeah, so 4 less than K actually means K minus 4. And I moved my numbers from the way it was written in English, which just super, it's not friendly. I understand that. But again, if you want to think about it with a number involved, I think most of the time you'll probably interpret it in the right way. So let's just say it said 4 less than 10. If it said 4 less than 10, what would you do? 10 minus 4. So if I replace the letter with a number, you're very likely inclined to do it in the proper way and not do it in the backwards way, okay? Product. Do you remember what the word product means?
Multiplication.
Multiplication. My son keeps saying timesing. No, son, stop. Can't say timesing. Product. Product means multiplication. So if it's the product of x and 5, we can actually write that as x times 5 if you want, like that. How else could you write it? You could write it as 5x. Okay? So the cool thing about addition and multiplication, and we'll talk more about this later, is that the order doesn't matter. That's why it's so nice to learn those facts when you're in elementary school, because once you get up to like the digits where you add nines to things, you already know all of them because you already did them all, right? Because you already did 1 plus 9 and 2 plus 9 and 3 plus 9. You added those up already. So when you get to the nines tables and you have to do 9 plus 1, we already know it. 9 plus 2, you already know it. So the same is true for multiplication. The order doesn't matter. That property is called commutative, and we'll talk more about it later. The last one's got the most going on. It says 14 more than twice a number. So go ahead. What do you have in mind? Okay, so you said 14 plus 2n. Did I hear you right? Okay, great. Yeah, that would work. When I have the phrase more than, it really doesn't matter where the addition is. Right? When I had the less than, I needed to make sure my order happened to switch. But it's perfectly okay to write the 14 plus here at the beginning. You could put it at the end if you wish. It doesn't matter, because addition doesn't matter on the order, like subtraction does. The twice a number. So you used n because we like n for numbers. I had a student that I tutored a long time, and she would always use her friends' names as the variables in her math problems. Don't know why. So you can use whatever variables you would like. I've been using x on the previous two, or on the previous one. They actually gave me the last two. They didn't give me one on C. So we can pick whatever we'd like. So twice a number. Well, twice a number means that I'm doubling it, right? So that's why I've got the 2n there, or the 2x, or whatever you choose. And then 14 more than is going to mean to add 14. Right? Any questions on those? Okay. So you're welcome to start working now then on your homework for this section. It's a little shorter, I think, than the last one. Figure out 21. It's only got us to 21 instead of like 26 or whatever the last one was. So we don't have quite as much time, but you still probably have plenty of time to finish it, at least maybe, or get a good start on it. So go ahead and start working on that. And then this one will be due on Monday.